The rapid development of radar during the Second World War provided many opportunities for peacetime exploitation, from air traffic control to police speed traps to medical scanning techniques. For me, one of the more interesting uses is the use of radar in astronomy. Radar astronomy, not to be confused with radio astronomy, uses passive observations of reflected radio signals that we've actually beamed out into space, as opposed to radio astronomy, which detects and measures naturally generated radio transmissions from such objects as the sun or other objects far out in the universe. The technique of radar astronomy was first developed and used in 1946, and the easiest object to start studying was, of course, the moon, as it's so close to us. And this gave rise to Project Diana. Diana, of course, being the goddess of the moon. Now, this was initiated in America in September 1945. And as you can see on the screen, here's an extract from Jack Mofinson, one of the engineers who was working on the project, in his paper Radio Echoes from the Moon, published in Electronics magazine in early 1946. The experiment briefly consisted of transmitting quarter-second pulses of radio frequency energy, radio waves, at 111.5 megacycles, or hertz as we would call them today, every 4 seconds in the direction of the moon, and then listening out around 2.5 seconds later for the echo. And these echoes were displayed both audibly and visibly. And there is a picture of the Project Diana site in New Jersey, next to a lake there. So technically, the experiment used the well-established radar systems that were evident during the war. But certain constants were radically different for the purposes of launching radio waves outside the Earth's atmosphere into space. Such things as the pulse width, which is the width of the radio pulse in seconds, the duration of it, and such things as the receiver sensitivity and transmitter power. Both had a major bearing on how strong the reflected signal would be. And of course, the precise frequency of the return signal, because lots of things are out there to try and change it. Doppler effect and other physical phenomena of radio signals passing through the atmosphere. So what did Project Diana actually achieve? Well, measurements included the level of surface roughness of the moon, and as sensitivity increased, the later mapping of shadowed regions near the poles of the moon. So what next? Well, it was 10 years before the technology was good enough to move on to the next easiest target, which is the planet Venus. This was of great scientific value if we could get a signal back from Venus, as it could prove a very accurate way to measure the size of what astronomers call the astronomical unit, which is simply the distance between the Earth and the Sun. Now, we've known roughly what this distance is right from the late 1700s. But in the age of sending spacecraft out into the solar system, we really needed to know this distance much more accurately to aid navigation between planets. Also, if we were able to measure the distance from the Earth to Venus, or the Earth to the Sun, such technical prowess would cause great kudos in public relations value. Because don't forget, then as now, funding for all this depended on politicians, and politicians depend on the public will. So if you get a public that's impressed with these activities, then funding will be a lot easier to obtain. So 1960, there was considerable pressure to squeeze scientific results from very weak and very noisy data that may or may not have come back as a reflection from Venus. And this was accomplished by very heavy post-processing of the received signals, which is not unlike putting in a few fuzzy pixels into a program like Photoshop and expecting the Mona Lisa in all her glory to come out the other end. And this was aided by the technique of expecting where to see an answer and you'll see it. And this led to early claims from American, British and Russian researchers, including our own Jodrell Bank, which are now known to be incorrect. Everyone agreed with each other because they knew where they were looking at the conventional value for the astronomical unit at the time, which was 149,467,000 kilometers. Perfectly accurate enough for what we want to do on Earth, but as I said before, not good enough for sending spacecraft around the solar system. So that was wrong. So the first real unambiguous detection of Venus is now known to be that made by the Jet Propulsion Laboratory on the 10th of March 1961, a year later. And using various types of data returned, a new value of 149,598,500 kilometers was determined and accepted as a new accurate value. And of course, once this was published, all the other groups jumped on the bandwagon, and by some strange coincidence, all their archived data showed echoes that did actually agree with these results. Strange that. So after Venus, what next? Well, Mercury, improved value of the distance from the Earth, and an estimate for the rotational period or the day length on Mercury, the amount of wobble or libration as we call it, and surface mapping, especially around the polar regions. So after Mercury, more detailed study of Venus, again the rotation period and the larger surface properties, because Venus is covered by a very thick, dense atmosphere, which means that we can't see through it. So even if we did send a spacecraft around it, we still wouldn't see the surface detail. So the Magellan probe was sent and mapped the entire planet using radar altimetry. And so we now know the main outline of the surface heights and topography of Venus. So this introduces the idea of sending spacecraft. So we can still do some measurements from the surface of the Earth, but now much better, we send out space probes to visit these areas. Even the Earth, so like the shuttle radar topography mission, mapped large parts of the surface of the Earth at a 30-meter resolution. And since it's been done to a much higher resolution. Mars, first of all, we did some surface roughness measurements using the Arecibo Observatory, which I'll talk about in a moment. But we've also sent a number of spacecraft to actually land on Mars, and the Mars Express mission carried a ground-penetrating radar to look on the subsurface of Mars. The Juno mission, for example, is one of the many satellites we've sent out to explore the Jupiter system and the major satellites, the Galilean satellites of Jupiter, and also the Saturn system, the Cassini spacecraft being the prime example there. But again, also we've used the Arecibo Observatory in Puerto Rico to study the rings and the largest moon of Saturn, Titan, before sending Cassini out there. And in fact, there is an image of the Arecibo Observatory in Puerto Rico. It makes use of a natural depression, most probably a meteor crater, an old meteor crater. You can see a dish has been built into this crater, and then permanent structures have been fixed around it for the focusing machinery there. Of course, being a fixed crater, you can't move it. So it does depend on the Earth moving for it to home in on whatever it's looking at or listening to. So here's an image of the Juno spacecraft with a list of the many instruments there, and the particular interest to us is the microwave radiometer in the red circle there, which is on the underside of the image as we can see it there. And then that leads on to what's left to observe in the solar system. and that's asteroids and comets. So what does radar do for us here? Well, it gives us the ability to study the shape, size, and how these things are spinning. Some of them have chaotic spins, others have nice ordered rotations. We do most of this from the ground, but we have sent 1 or 2 spacecraft specifically to meet up and even land on various asteroids and comets. But as I said, the main exploration is done from the Earth, and again, mainly from Arecibo. And we're getting radar imaging. The technology is to such a state now, we're getting 7.5 meter resolution on these targets. As I say, we can look at the size, shape, spin, and the radar albedo. That's simply the reflective power of the radio beam that hits it. And we can extract that from the signals. And in fact, by 2018, 138 main belt asteroids, these are the major asteroids that are pretty much stay between the orbits of Mars and Jupiter. But more importantly, 789 near-Earth asteroids. These are asteroids, lumps of rock, that travel around the sun, but in a much more eccentric orbit. And some of these actually come very close to the Earth's orbit. And also 20 comets have been observed. So many bodies, these near-Earth objects, have been observed as they fly close by the Earth. Now this is important because although we can't do too much about it at the moment, it's nice to know if we are going to be hit by one of these objects. And it was one such of these objects that's thought to have hit the Earth and caused the extinction event which wiped out the dinosaurs. So at the moment, all we can do is to look out for these, but it'll be another few decades before perhaps we can do anything about it. So here's an image of one of these asteroids, Cleopatra, based on radar analysis. This is, funnily enough, called the Dogbone asteroid. So by way of summing up, from the early wartime days of using radar to detect incoming enemy planes, to the modern day detection and investigation of potential threats to the Earth from near-Earth asteroids, we do have a lot to thank radar for. There's a lot more information on the development and use of radar during and after the war on the Bawdsey Radar Museum website. Just search for Bawdsey Radar.